Racing Against the Sunset by Philip Wesley. And now we've had the sunset, we've had a nice evening, and it's morning, and we are now going to play Ocean of Color by Philip Wesley. And I'm changing levers. I play a Lion and Healy lever 40 harp, so there's 40 strings here. And I change the notes here with my hands. If I had a pedal harp, I'd be using my feet. But so without further ado, here is Ocean of Color. Okay, Ocean of Color. Ocean of Color by Philip Wesley. Okay, we go with Equestrian Trails.
Okay. I can hear it enough to know when she's coming to an end. Should be good. Kim, are you about at a stopping point? I'm sorry to break in. It's so beautiful. I really appreciate the fact that you are presenting us with this wonderful music each month. Thank you so much
for having me. It's been a pleasure.
Thank you. And welcome everybody to the June meeting of Orange County Astronomers. Can you believe that we are about halfway through the year already? It's just amazing. And we do have a wonderful program ready to go tonight. And so far, our technical difficulties have all been. Can everybody in the auditorium hear what I'm saying? Okay, people at the back are raising their thumb. Raisa, if you can't hear over there, let me know. Okay, good. I think our technical difficulties actually are a lot less than they have been in past months, which is wonderful. And however, our usual announcement person, unfortunately, cannot be with us this month. So Doug Millar and I will undertake to do the club announcements this month.
Our announcement person is at Madison Square Garden doing an internship.
I'm advised that our regular announcement person, Kyle, is doing here. I will get this to Doug, who I think knows the details.
You know, the musician, but he is doing an internship at Madison Square Garden this summer, a plum position. So he's moving his career along, but he's still involved in the club. And sends regards, but it's up to Barb and I tonight.
Okay. We're now on. We're switching slideshows here. Well, you'll be happy to know that this worked really, really well a couple of times when we were trying it before we actually went live. Why
Actually,
does that
Barbara, I have the slideshow up if you're looking at the screen.
Oh, you do? Okay, then I will tell Sam not to.
Yeah, I'm sharing the screen right now.
Okay, great. Can you unshare it? Stop share. Okay. It's going through automatically, Alan.
No, it's not.
Oh, okay. Could you go? Okay, this is at the
That's the welcome. Yeah.
Okay, so you've already had the welcome, so we can go to slide number 2, which is welcome to new members, which is a separate welcome. And any of the new members who are here, welcome to the club. We're really glad to have you. The 4, as you can see up on the screen, are Jacob Bamati, Joe Goddard, John Mayfield, and Silva Reese. Those who were here can pick up their badges on the badge board that's down on the whiteboard. Those who are not, Charlie will be sending those along to you probably within a couple months at the latest. If you don't receive them, feel free to send Charlie an email and he can figure out what's going on. Okay, next slide. Okay, we have star parties actually coming up. Well, we have the star party for June coming up June 17th. The star party for July is being featured on this because that is going to be our annual Starbecue, and we do like people to be aware of it well in advance. That's where people, it's a potluck. It's a potluck we had to give up during COVID. We had it last year for the first time since COVID, and we are looking forward to having it again this year. So again, that'll be the July Star Party, July 15th. Bring a dish, come out to Anza. We usually get started sometime after 5 o'clock. It's up at the observatory on the shady side of the observatory, because that's the largest patch of shade on the site. And a great time is had by all, and then we all go and do whatever we're going to do for our usual evening activities. So we look forward to seeing you there. And the Orange County Star Parties, we are still trying to work out a few bugs, and hopefully we'll have dates for you before too long. Special interest groups, Astrophysics has been meeting regularly. They're back at the Heritage Museum. Their next meeting is a week from tonight, June 16th. Feel free to attend and to contact the coordinator if you've got any questions. It's a really fun group. And if you have any interest in astrophysics or learning more about why what's up there is up there, astrophysics is the place to go. The beginners class, it was last Friday night. The next one is July 7th. That will also, I believe there's a slide on this coming up. That will also be our how to use your telescope night, which we do twice a year. We can use volunteers out at the Heritage Museum to help people that come in for some help with their telescopes. If you've got a telescope that you'd like a bit of help with, that's the time and the place to bring it. I think we usually have the gates open by around 7 o'clock, and things really are starting to go by 7:30. So if you have questions about that, check the website for the email addresses to send them to, and we'll look forward to seeing you out there. The next OCA board meeting, which is not to be overlooked, is July 30th, end of July. And those are always fun events. Members, believe it or not, are welcome. Honest. We haven't had members actually attend unless they wanted us to do something or look at something for them. But, you know, in the past, we've actually had board watchers who showed up to find out what we were doing and maybe offer a few words of wisdom and that sort of thing. If that at all interests you, or you just want to find out what we're doing, you know, please feel free to let us know, and you can be added to the Zoom call for it. That means you don't even have to travel anywhere. You can do it from the pleasant confines of your own home.
And if you decide to attend, you'll not automatically be volunteered as a board member.
Though it is always a good idea to be thinking about who you might want to, you know, it's a good idea to start thinking about running for the next board, because we do it every year.
Our next slide. Okay, beginners class. If you're a person with a telescope and you are up against the wall about how to use the telescope, go to the beginners class. There'll be lots of people that will help you out. And
this is actually for the one for next month.
Yeah, for July. And I can't overstate the importance of doing that, because most people get into astronomy, buy a telescope and can't figure out how to use it, put it in the closet and never go back again. This is a way to get past that one choke point and actually see something and use something with a telescope. Okay. Next. OVRO. OVRO is going to be June 23rd, Friday, Saturday, and Sunday. You don't have to come on Friday, but since it's a full night of dark sky observing, I suggest it. The program starts at 1 o'clock on Saturday, followed by dinner at Bishop at the We Toss'em They're Awesome Pizza Factory. And then another night full of observing. And then Sundays, you're on your own to do what you like. How many people here tonight are thinking about going to OVRO? 1, 2, 3, 4, 5. Good. This is something that we've arranged with the Owens Valley Radio Observatory. We have no idea how long we are going to be in this aura of cooperation. So make hay while the sun shines. If you have any information, need any information, look on the back of your Serious Astronomer, look for Doug Millar, and email me. I'll be glad to talk to you and send you some information. Okay.
Okay, we talked about this. We actually put in a reminder here. And you'll be reminded again, presumably next month, since this meeting should happen before the barbecue. But do start thinking about what you want to bring. Outreach events. If you're at all interested in helping out with the outreach program, Jeff Gray is the guy to contact. He's been very innovative and really is excited about outreach. So I think you'd like working with him. And his contact information is not just there, but actually back of Serious Astronomer and on the website. The coffee stand. Now, this is a thing that actually is more for those of us that are here in person, which is sort of a reminder that those of you who are not here in person are missing out a little bit. The coffee stand is upstairs, and it's Helen's Coffee Corner at this point. The coffee is good, the donuts are excellent, and a great time is had by all up there. I have frequently seen very active groups having animated discussions with good food. The Adoptoscope program. Don't move away.
We're trading off the announcements. The Adoptoscope program is something John Hoot put together to make use of telescopes. And one of the problems is that there are lots of telescopes sitting in closets. This is an assortment of telescopes that are open for adoption with a possibility of buying one. So if you're considering getting a telescope and you kind of don't know what one to do, talk to John and you can adopt a scope. If you don't like it, actually, I was adopted as a child. And as far as I know, there wasn't any option to send me back. Although my mother did claim that I would go back to certain populations of obscure people if I didn't rectify my behavior. But it ended when she said, I'm going to send you back to the Indians. And I said, I'd like to go to the Ojibways. And I don't remember what happened after that, but I didn't go to the Ojibways. And I got a telescope. So if you're interested in a telescope, we have a wide variety of telescopes, and John Hoot is a guy to talk to, and they're at severe discounts. Dave Fisher is our editor of the Serious Astronomer. He's always looking for articles. Even if it's like you go to ANZA and have a nice night observing M7, write it up. Tell us what a nice time you had and why and what you learned about it, even if it's a couple of paragraphs, and send it in to Dave, and he'll fluff it up and make sure it's presentable and publish it. So please help him out. And you need to tell us whether you want to get to the Serious Astronomer by email or by snail mail. That helps and makes it more convenient for you. Clearance. And we're not talking about the green stuff that you pay a lot of money at the dispensary for.
Yes, we keep harping on this. People might have remembered that even though winter is now receding behind us, it was a very wet winter. The local weed population really liked the wet winter. We are also expecting it may be a kind of a wet summer, actually, because it looks like monsoon activity has started early. What this means in terms of our ANZA site is that we not only have a good, healthy crop of weeds, the grasses out there are growing phenomenally, but we are expecting that we will have continued growth over the summer and into the fall. So if you're out at ANZA and, planning to go out there, take some, weeding or cutting implements with you and help with the weed clearance. We need to keep the buildings as clear as possible, and also the pads and other structures. Simply that will minimize the chance that we will actually have any kind of fire problems coming through. And it also does reduce the chance that you will have an unobserved approach to wildlife you don't particularly want to approach, like snakes or rats or mice or whatever. So again, any help you can give, that would be really great. There may be some tools in the storage area behind the club observatory. I'm not sure what condition they're in, and I don't know if there's anything down at ANZA House, but when I'm out there next time, I can check. The question we had was, what do we do with the weeds that we have when you cut them down? preferably, if you could cart them away, that would be helpful. There are some areas on the site that some can be dumped, like in some culvert areas to help keep, minimize erosion. But the thing to remember out there is that things do not break down very quickly because overall it is a semi-arid environment. And so even things that would break down at the coast very rapidly, they don't there. They'll last for years. As I said, the best thing to do is take it with you or take it to the dump site, but that's in Anza, and most people don't want to take that extra time. But thank you. And tonight's moon, in case you hadn't noticed, is a waning crescent, or waning gibbous, it says. Okay, I haven't been able to see the moon, so I have no idea. And the main presentation will be along presently, but before that, we have What's Up with John Garrett, who is our beloved presenter from our neighboring club, the Temecula Valley Astronomers. And so please welcome John, and I'll turn it over to him.
Thank you. That's really nice. Is it possible to dim the lights in here just a little bit? Yeah, most of what I'm going to show you is a lot of pictures that I've taken. The pictures, I've taken a lot of wide field pictures, and I have a very basic camera that I do that with. And then one of the things I enjoy doing most is when I get a wide field picture that's got fairly good contrast, I like to just look at it and compare it to printed star charts to see if I could see what's in there. And that helps me discover a lot of things. Once I discover a few things in the star chart and often see them in my own wide field pictures, I like to then use small telescope, a 3-inch refractor, and just see if I can get that object in like a 30-second photo. And I often use 30-second or a little bit longer exposures with a very small telescope because it's very forgiving. I don't track. I'm not that sophisticated. I usually just set up my telescope on my backyard balcony, and between moments where cars drive by, which will jiggle the balcony and will show up my photographs, about 30 seconds, I usually can get something. And it kind of gives you an idea of what you might see in a pair of binoculars. I also have an 8-inch telescope that I couple with that, and I sometimes try to get exposures through that telescope, and that's getting a little more difficult, but it's kind of fun. I like to see what I can capture in a wide field view, what I can get in a small telescope, which is comparable to the field of view that you get with a high-powered pair of binoculars. And then I like to do things, I'm starting to work into higher power, but very, very slowly. So anyway, I should preface everything that I'm going to say to you is weather permitting. I don't know about you, but I've only had a few days since the last meeting I was here that were clear enough to see anything. One of them was my son's high school graduation, so I was a little conflicted there, but I think I did the right choice and went to the graduation. Last night was a rare night, and I did get some images last night, but otherwise, it's really been a while. So is this ready? Are we ready? Okay, I'm still talking. We're about ready. But anyway, yeah, I had a few days back in May. When there was, looks like I'm up. Ready to go? I'm good. Okay. So now we start the little what's up. So, okay. Help. Okay. Well, as you might have known, there was a supernova on May 19th. And so here's a picture that I took of it with my 3-inch telescope, and I don't think you can really see what's there very easily, but in this next image I've marked the location of the supernova in Messier object M101. Now, last month when I was here, I was recommending things in the sky, and M101 was one of them, and my existing picture of M101 was pretty pathetic. So on May 19th, I actually wanted to set up my telescope, but weather permitting, I wasn't able to. And if I had set up my telescope on May 19th, when the supernova was discovered, I'm certain I would have tried to image M101. And if I had done that, I would have been one of the first people to observe that supernova. And that's as close as I've ever come to discovering a supernova. So I feel pretty good about getting that close. But anyway, I didn't, of course, but anyway, 2 days later, the weather did clear up, and then I did get this image through my small refractor. And here it is from last night. So it's still there. So if you look at the previous image and got those little arrows marked, and right there from last night with the same telescope, it's still visible. So if you're worried about missing the supernova in M101, it's still there. It's still fairly bright, and it does show up on a minute exposure with my 3-inch refractor. And here, yeah, there I marked it. And here here's one that I got last month in my 8-inch scope. And there it is, the supernova. So that's still something to look for. So if you do get a clear night, you might want to try your hand in seeing it visually with a 8-inch or larger telescope. You might want to photograph it. Comes out pretty easy. Scorpius, no, the back. We'll actually see Scorpius later. I'll come to a few slides with that. And so, but this particular field of view that you see is actually a little narrower than what you'd get like in a 10 power pair of binoculars. So Scorpius is a ways off from that. Anyway, if you have solar filter, you might find the sun interesting because, you know, the nights have been clouded out, but the sun's been very active lately. So here's one, some sun from some sunspots that I took a few weeks ago. And then I did get a little bit of clearing last night, so I could confirm that the planets Venus and Mars are still visible in the evening sky. So here's from my balcony. They're just clearing my tree in the backyard. The constellation Gemini is nearby, and here is the planet Venus, and here's the planet Mars. Venus is going to stick around for a while. Over the next month, it's going to reach almost its maximum size, so you can watch that through a telescope. And since my last month was pretty cloudy, I didn't get out to do any fresh photographs of the night sky. So this turned out to be a good recent month for me to go through my archives and find what I photographed in the past. So about 10 years ago, I borrowed a friend's 8mm lens and took a picture of the sky at Palomar Observatory Campground. And so this is what the sky might look like at 9 or 10 o'clock in the evening at that location. And this is a very wide field lens. So it's covering most of the sky. As you can look at the trees on the side, they're pointing sideways, and they're on the other side, they're pointing that way. So that's a sign that you're kind of getting a big fisheye effect with a very wide field lens. But here's some of the, oh, by the way, I always thought the Milky Way in these pictures looks a bit like a dragon. So there's my interpretation of a dragon. Anyway, so here's a bunch of constellations that you'll see in the sky tonight, and I'm going to cover a few of them. Sagittarius is way over there in the south, but it looks like Sagittarius is up on the right, but it's actually in the southern sky. And of course, Sagittarius is shooting an arrow at Scorpius. So there's Scorpius off that. And then above them, off Eucus, the serpent bearer. I've only drawn the serpent. That's the easier part to draw. And a few other bird constellations in the along the Milky Way, Aquila the eagle and Cygnus the swan. And then Hercules, that butterfly-shaped object kind of high in the middle. And then Draco off to the right. I'm going to take mostly the top half of this photo and going through some of the things to look at. So here's the area of Sagittarius and Scorpius. And here's a photo I took of them several years ago when the weather was permitting. And it's the only region of the sky that I've noticed that sometimes it's too bright for my drawings. So I actually toned this one down a little bit because I wanted a little better contrast when I brought up the constellations. And so here's the classic scene of the archer who was supposedly sent to slay the scorpion. But if you take away the archer, you can see Sagittarius by the very teapot shape. And I consider that evidence that we actually live in a good age to be alive, because, you know, people 2,000 years ago looked at this and go, oh my God, that's definitely a person with a bow and arrow shooting a giant scorpion. Whereas today we look at it and go, huh, tea time. And so we think of teapot, and there's that brightest part of the galaxy is right there where the steam would be coming out of the teapot. Anyway, here's a bunch of deep sky objects in that region. And all of these from a dark location, I think are visible in a pair of binoculars and even better in a telescope. So what I'm going to do is run through a whole bunch of them that I've taken with my 3-inch refractor. And most of these are like 30 to a minute exposures. And so here's one of the brighter ones, M4. That's the one that's in Scorpius off there, right? You can see in Scorpius, M4. And then M6. That one looks a little cloudy, like a little cloud in the pair of binoculars. But once you put it in a telescope, you can see it's a bunch of stars. M7, as mentioned earlier by Doug, nice, beautiful star cluster with a lot of Milky Way in the background. And then the objects M8 and M20, and you can get the two of them in a wide field of view. And M22, a very stunning globular cluster, and M23 and M24 star cloud, and then M25. So there's a lot of beautiful things in that. And even these nebula show up in a pair of binoculars at a dark location, 16 and M17. So taking that area of the sky, but there's also some other globular clusters right over here in Ophiuchus. I haven't actually looked at M107. So M107's on my to-do list, but I did have M9 in my collection. And as I was looking at it and preparing for this talk, I realized, oh, I got those other two NGC globular clusters. So this is an area where you could get 3 globular clusters, probably within the same field of view at low power. And if we go a little farther, they're just near that same area are one of my personal favorite objects to hunt down, and that is planetary nebula, which are essentially stars, smaller stars like our sun that have died and have created these beautiful little nebula. And those ones that I've just shown here are actually on my to-do list. I don't have any images of them yet. But so from there, we looked at that part of the sky. Now we're going to look at this part of the sky. A couple years after I took this photograph, borrowing a friend's 8mm lens, I bought myself a very cheap 14mm lens. And so I had a very magic couple years where I was taking really wide field shots with my 14mm lens, which it takes up about that much of the sky, until I dropped it. And ironically, after I dropped it, it would focus on infinity. It would focus up close, but not on infinity. And I would have been happy if it just happened the other way around. But I still had one of those photos taken at the same location. If you see those trees, they're the same trees that are in this photo. And here's the constellation Hercules, tends to look like a big butterfly. And above Corona Borealis and Boötes, and down below it, the constellation Lyra. Off to the right, Draco the dragon. And I have a little picture of the Draco the dragon. And here's how I'm interpreting Hercules. I think he kind of looks like a weightlifter on a bench. So anyway, so here's Ophiuchus. I'll start with there. And Ophiuchus is riddled with globular clusters, and some of them I've created images of. M5, a very bright and beautiful one up there, and then M10 and M12. Both of these were taken in my semi-polluted light sky, light polluted front yard. So I'm pretty sure they'd be visible in telescopes. And then M14, and then from there, there's also a unique object called Barnard's star. That is a red dwarf that is known to be like one of the closest stars to us. And it's the only ones that are closer are the Alpha Centauri system. And that one is noted for a very fast, proper motion. And that is, you can actually track its motion against the other stars in a matter of years. So if you take a picture of it now, and you have another cloudy month where you're going through your archive 5 or 10 years later, take another picture, you might actually be able to track proper motion by getting a photograph of that area. And then just under it is another one, NGC 6572, and that's a planetary nebula. And there I have it marked with my little red marker. And when you look at it, you go, well, it looks like a little green dot. Well, that's really about what it looks like in my 3-inch scope. And even in my 8-inch scope, it looks like a little green dot. And I find that kind of neat. The Hercules, if we move on to Hercules, a number of planetary nebula and globular clusters in Hercules. And so here's one of the planetary nebula. Again, it looks like a green dot. And here's a little bigger version of the green dot in my 8-inch scope. And then here another green dot and another green dot. Then IC 4598 is actually fairly bright, and it shows up pretty well in both too. And then 629 in Hercules, a globular cluster, my 3-inch scope, and M92 and M92 in my bigger scope, and then M13 in Hercules. And that was probably one of the first pictures I ever took. And so I've long lost whatever my imaging details were. And so I've got to go back and record my, and take a better picture next time. Oh, also right next to M13, you might see a small galaxy. Was it 6207? And so from Hercules, you can go on over to Draco and Lyra. And there are two also very good planetary nebula in those. And here is the one in Draco, NGC 6543. And the one here is an M57 that's well known as the Ring Nebula, but that's taken through a 3-inch scope, and you can just barely detect that it's a ring. So it's just kind of fun to take a picture at low power and go, oh wow, I can actually see the ring. And here it is with a slightly bigger field of, slightly more magnification. And I just started learning how to stack photos. So I'm getting a few of these where I can actually get them stacked well enough that I can bring out stuff that wasn't, showing up at just a 30-second exposure. But anyway, beautiful sky. I kind of went off the beaten path. If you consider the Milky Way the beaten path, I went off just to the side of it because there's a lot of stuff that gets missed because of the focus people put on the Milky Way, which is quite understandable. So I hope you get out to see any or all of those, of course, weather permitting. So thank you. Yeah, it's free.
Okay, I guess we lost the question.
What he said was he used Registax.
Okay, perfect. So let me thank John for a wonderful presentation. Looking forward to see more of this in the upcoming months. Hi, everybody. My name is Reza, and I'm the Vice President of the club. I, too, would like to welcome you to this general meeting of the Orange County Astronomers on June 9th, 2023. Our speaker at this meeting received his PhD in astronomy from University of St. Andrews in 2000. Following his doctorate, he was a founding member of the SuperWASP Transit Survey, searching for extrasolar planets, for which he received the RAS Group Achievement Award. Since joining the Las Cumbres Observatory in 2007, he has worked on building pipelines and data archives for the observatory, confirming new transiting extrasolar planets, and building a new science group for the study of solar system objects. He is currently co-lead of the LCO Outbursting Objects Key (LOOK) project to study the behavior of comets for ESA's Comet Interceptor mission, and a member of NASA's Double Asteroid Redirection Test (DART) investigation team. Please join me in welcoming Dr. Tim Lister. Tim.
Thank you very much, folks. Let's get this up and going. Okay. Hopefully everybody can hear me and see the slides.
Yes.
Excellent. Hi, so thank you for giving me a chance to talk to you tonight about this exciting mission that I and LCO have been involved in. So tonight I'd like to tell you a little bit about near-Earth objects, the risk that they can pose to the Earth, and the DART mission, which is NASA and the world's first mission for planetary defense. So DART is a NASA mission, but like most projects in science, it involves a lot of different partner institutions. One of these is LCO, or Las Cumbres Observatory, which I work for, and I'll be telling you more about our involvement later. So some of you may have heard something in the news last year about NASA deliberately crashing a spacecraft into an asteroid and deflecting it with a mission called DART. But these last 8 months since the DART impact are just the end of a multi-year journey, which is not over yet. To give you a short overview and see why we started on this long journey through space and time, I'd like to play you this short video, which condenses the whole mission down into just a few minutes.
We're embarking on a new era of humankind.
Didymos and Dimorphos make a great target. We needed an asteroid with a moon that you can see from ground-based telescopes around the world.
We're doing this mission to prove that we can deflect an asteroid.
5, 4, 3, 2, 1. And liftoff of the Falcon 9 and DART on NASA's first planetary defense test to intentionally crash into an asteroid.
Even if we do everything right, our sensors work well, our spacecraft is doing well, even then, we might still miss.
4, 3, 2, 1.
For the first time ever, humanity has changed the orbit of a planetary object.
NASA confirms that DART successfully changed the targeted asteroid's trajectory.
Using the ground-based telescopes around the world to watch the system and see how it's affected by this impact event.
This is a watershed moment for planetary defense and a watershed moment for humanity.
Okay, so I have to give a shout out to the NASA communications folks who are really great at putting together really inspiring videos. And this graphic is the jam-packed summary of everything that's been going on with the DART mission, which I'm going to break down and explain to you in more detail. So as you saw in the video, we launched the DART spacecraft in November 2021 from Vandenberg Space Force Base. This is just up the road from me here in Santa Barbara. We sent the spacecraft off on a collision course with the Didymos binary asteroid system. This consists of a primary or main body Didymos, which is almost 800 meters in diameter, and the smaller secondary, which we used to call by the nickname of Didymoon, but it's now officially called Dimorphos. Dimorphos is quite a bit smaller than Didymos. We now know it's about 150 meters across, but we'd never seen Dimorphos before DART got there, and only had estimates on its size before. So Dimorphos goes around in its orbit, its path in space around Didymos in a little under 12 hours, and it's this change in period that we measured from observatories on Earth that told us we had deflected Dimorphos and how much momentum or push the spacecraft actually gave to Dimorphos. The DART spacecraft collided head-on with Dimorphos at 14,000 miles per hour, or about 6 kilometers per second. But first, let's back up and see why we might want to crash an expensive asteroid into an expensive spacecraft into an asteroid in the first place. So if we were able to look down on our solar system from above and plot out the paths or orbits of things we know about near the Earth, it would look a little something like this. We can see the Sun in the center and the inner planets of Mercury, Venus, Earth, and Mars on here. Every other line on here is a near-Earth object, or a NEO, and specifically these are what's called potentially hazardous objects. This means that they are larger than 140 meters in size, and they could come close enough to the Earth in the future that they could potentially threaten the Earth. I don't want anyone to worry. I want to stress at this point that we know where all of these 2,200 asteroids are, and no known asteroid is a threat to hit the Earth in the next century. But how do we know that there are things out there that aren't watching where they're going and could run into the Earth or other planets? If we look up at the moon, and this is an easy experiment you can do yourself, we can see that the moon is covered in craters, as shown in these images on the left, taken by the Lunar Reconnaissance Orbiter. If we actually measure the height of the moon's surface, as shown in this image on the right, then these craters stand out even more clearly. This big purpley area at the bottom on the far side of the moon is what's called the South Pole Aitken Basin. It's one of the biggest impact craters we know of in the whole solar system. So we've seen that the moon has been hit a lot. So what about the Earth? After all, the Earth is a bigger target than the Moon, and we've also grown quite attached to it because it's our home. It's a little trickier on Earth as we have oceans, glaciers, and weather, which will try and hide and erase impact craters. But if we look carefully, we can find them, like this one in Algeria that was actually taken from the International Space Station. Also, we can detect smaller asteroids that explode in the upper atmosphere. This map shows all of the fireballs that have been found by US government sensors. This is the official way of saying the things that look for people testing nukes. Most of these fireballs are quite small, but they're still equivalent to 1,000 tons of TNT. And to give you a sort of sense of perspective, the large explosion that occurred in the port of Beirut in 2020 was equivalent to about 800 tons of TNT. You've probably noticed this big red circle up here. Well, this was the airburst that occurred over the Russian city of Chelyabinsk in 2013. This was caused by a roughly 20-meter asteroid, which approached from the direction of the sun, so we had no warning. It caused a large explosion over the city that resulted in about 1,500 people needing medical treatment, mostly for flying glass injuries from the blast wave. One of the famous asteroid impact craters that people may have heard of is so-called Barringer or Meteor Crater, which is out in the desert in Arizona. This is an image from the air. This was formed about 50,000 years ago by a 50-meter diameter metallic asteroid. The crater is almost a mile across, and it's several hundred feet in diameter. On the right, it shows the effects of what would have happened during the impact. We would have had a fireball that went out to about 10 kilometers or 6 miles distance. Large animals would have been killed or injured out to sort of 15 miles or 24 kilometers distance. And there would have been hurricane force winds from the blast out to nearly 25 miles away from the impact. But maybe we don't care about random bits of Arizona desert, but what would happen if something this size impacted over a city? So during the 2019 Planetary Defense Conference, this brings together astronomers, engineers, and people from the civil defense agencies and FEMA. We did a role play exercise of how we would respond to a simulated asteroid threat. Well, this particular simulated exercise ended with a 60-meter asteroid impacting over Central Park in New York with a force of 15 million tons of TNT equivalent. Everything inside this red zone, which covers most of Manhattan, would be completely destroyed. Everything inside this much larger orange zone, most residential structures like your house, would collapse, and your clothing would actually ignite from the fireball. Even out in this green zone at more than 30 kilometers away from the impact zone, and green definitely doesn't mean good here, windows would break from the overpressure of the blast wave, and your exposed skin could be burnt or blistered. So these are pretty serious effects. So how many of objects of a particular size are there? For the ones that cause the fireballs and that we saw on the map earlier, these are a couple of meters in size. One of these hits the Earth about once per year. It produces a bright flash in the upper atmosphere, doesn't normally cause any ground effects, but can leave meteorites, as happened recently with the one in northern France. By modeling asteroids and other bodies in the solar system, we can make estimates of how many objects of a particular size are out there, and we can adjust these models based on how many objects of a particular size we've seen. From this, we know that there's about 500 million objects of this sort of 4 meter size, and we've found less than 0.1% of them. If we go up in size to 25 meters, which is about the size of the Chelyabinsk impactor, one of these hits the Earth about every century. These cause an airburst explosion, and as we saw with Chelyabinsk, could cause widespread injuries if this happened over a populated area. We think there's about 5 million of these objects out there, and we've found less than 1% of them. They're very, very difficult to see. Going up to the other end, The other asteroid impact a lot of people have heard of is the so-called dinosaur killer, the Chicxulub impactor. We think this was about a 10-kilometer asteroid which slammed into the Yucatan Peninsula of Mexico about 65 million years ago. Fortunately, these objects don't hit the Earth very often, only every 100 to 200 million years, because these can cause global devastation and mass extinction of terrestrial life. Fortunately, there's only about 4 of these objects, and we've found all of them. If we come down in size to about 1 kilometer, one of these will hit the Earth about every 500,000 years. These again will cause global devastation, a sort of 10-kilometer crater. And we think there's about 900 of these left. Fortunately, we've found the vast majority of them, over 95%, and the future sky surveys will find the remainder. If you come down again in size to sort of 140 meters, which if you remember is about the size of Dimorphos, one of these hits the Earth about every 25,000 years. This will cause a sort of 1 to 2 kilometer crater, which could be deadly if it occurred over a large metropolitan area like Los Angeles or over a small state, and cause mass casualties. We think there's about 20,000 of these objects, and we've found a little over 40% of them. So what can we do if we were to find an asteroid on a collision course? Depending on how big it is and how much warning we have, we do actually have a variety of options. For the most likely size of asteroid that we would need to launch a mitigation mission for, which is in the 75 to 200 meter size, a kinetic impactor is our best option. And this is exactly why it was recommended as the first priority for a planetary defense mission, and where DART comes in and what DART will test. Some of you may have noticed the big red area labeled nuclear up here, or remember a certain movie starring Bruce Willis and wondering why we don't just nuke the asteroid. Part of the problem with that, which I'll come back to later, is that we often don't have a very good sense of how strong the asteroid is and how well it's held together. If we blow it up with a nuke, we might just disrupt it rather than actually pushing it off course, and what we're just left with is just a whole bunch of slightly smaller asteroids instead. So Dimorphos is right in the middle of the size range where a kinetic impactor is effective. It's roughly the size of the Great Pyramid of Giza, or a little under twice the size of the Statue of Liberty. Didymos is a whole lot bigger. It's about 800 meters across, or nearly half a mile across. It's about the size of the Burj Khalifa skyscraper in Dubai. The spacecraft itself, DART, is about the size of a mini fridge. It's about a 4-foot cube, but it's got these big solar arrays on the side, and when they're unrolled, it becomes about the size of a school bus. And so wanting to do a kinetic deflection test on something the size of Dimorphos is what set the DART mission's top-level requirements. The first one is kind of obvious, but we actually have to hit and impact Dimorphos. And specifically, we wanted to do this during September and October of 2022, when Didymos was close to the Earth. We wanted to change the binary orbital period of Dimorphos around Didymos by at least 73 seconds. And we wanted to be able to measure this change in the orbital period to 10% or 7 seconds from observatories on the ground, both before and after the impact. And this will let us get the period change, and this lets us get to this thing which we call beta. Beta is the momentum enhancement factor. It tells us how much extra push we gave Dimorphos above what we got from the spacecraft alone. This allows us to characterize the impact site and the dynamics of the ejector and the properties of the asteroid. And this is vitally important if we're going to do planetary deflection for real in the future. And this was the ideal time to be doing this mission, when Didymos was close to the Earth in September and October of 2022, when we can get to it with a spacecraft. So we launched the spacecraft on November 23rd, and it traveled around in this very similar orbit to the Earth, and then headed out to Didymos, which is this much longer, larger, and more eccentric orbit. And this carried on until the spacecraft and Didymos met up on September the 26th, 2022. And the reason why the Didymos system is the ideal target for doing this test is it allows us to test deflecting an asteroid that's of the size that's most hazardous, but without any risk to the Earth. Because we know Didymos is not going to hit the Earth, and because we're hitting Dimorphos and not Didymos itself, we know we won't alter Didymos's orbit and potentially deflect it onto a collision course with the Earth. Also, measuring this change in the period of a binary asteroid is much, much easier than trying to measure the deflection of the much more massive Didymos itself if we'd hit that instead. That worked okay on Zoom. So DART's only instrument is Draco. It uses an 8-inch diameter telescope and a CMOS imaging sensor, which is similar to what a lot of amateurs use. It began to image the Didymos system about 30 days before DART hit Dimorphos, and this is a movie of the optical navigation images coming from Draco over the last 30 days. And you can see Didymos getting slowly brighter and brighter in the days up to impact. So although we were only able to actually detect Didymos in single images 30 days out, by stacking up 243 images together when the spacecraft was 20 million miles and 61 days out, we were able to make our first detection of the Didymos system with DART and Draco. It's always good when you can confirm your spacecraft can actually see its target. And this was one of the major challenges of the mission. How do you make a spacecraft crash into a target you've only ever seen as a point of light before? Although Didymos was fairly close to the Earth, as I said, the round trip time was still far too long. We couldn't have somebody like with an Xbox controller steering DART into Dimorphos. The spacecraft would have to autonomously navigate itself. This system was called SmartNav. We switched this on about 4 hours before impact when DART was still 90,000 kilometers away from Didymos, and it was still just a single pixel. Just over an hour before impact was the first time that we'd ever seen Dimorphos as a separate object. This was when Dimorphos came out from behind the back of Didymos, and we could actually see it as a separate object. And at this point, SmartNav retargeted the spacecraft to aim for Dimorphos rather than for Didymos, and it was firing the thrusters to keep the spacecraft on course for Dimorphos. SmartNav stopped firing its thrusters about 2.5 minutes before impact, and after that, it was just gliding into impact. I say glide, this glide is still 14,000 miles an hour or 6 kilometers a second. So this means the last complete image we got was 2 seconds out from a distance of 12 kilometers. So from this analogy and the quote here, you can tell that DART was built on the East Coast at APL, but for us left coast baseball fans, the equivalent is if we stopped maneuvering around Redding in Northern California and glided in to land inside something the size of Angel Stadium. So these are the last 5.5 minutes of the mission. These are the raw images coming back from Draco as they were shown live during the webcast. Draco is taking images about once per second, and you can see the SmartNav adjusting the aim point, and then from about 2 minutes to go, that settles down and we're just heading straight in for the target. So these are sped up by a factor of 10 times until we get to the final images, and those are just in real time. And this was the very last image we got, which was only a partial image, and this confirmed that we'd actually hit, and this was loss of signal. So these are the images of Dimorphos on the left and Didymos on the right to scale about 2.5 minutes before impact. Didymos looks pretty close to what we expected from the radar shape models we'd made before. Last time it was close to the Earth, but it's a bit more flattened than we expected. It's got this very similar spinning top shape that we've seen from other near-Earth asteroids like Ryugu and Bennu that have also been visited by spacecraft. Dimorphos is quite a lot rounder. It looks kind of like a peanut M&M. Some people have also said it looks a little like a fish with the tail over here on the right and the fish nose sticking out over on the left. What we can say is that although Dimorphos is only 150 meters across, there's some pretty massive boulders we can see on it, including the fish nose itself. And these large boulders at the top near the limb, we can just see this big one around the sort of 10 o'clock position poking over the limb. These are clearly many meters across. This is our final complete image. This covers about 100 feet across, or 31 meters. And we can see that there's boulders, some of which are quite large, and they're close to where we impacted. And we can see down to much smaller material on the surface on this. Things are all scales from meters down to centimeters and things below the resolution limit of the camera. As I say, this was taken 2 seconds before impact at a distance of 12 kilometers. And this is our compilation of all of the final images with the time before impact and the pixel scale that's shown. We go from about 35 centimeters per pixel in the top left image, which shows all of Dimorphos, down to just a few centimeters per pixel in the final images. And if we layer all of the images together, we can get this high resolution view of Dimorphos. So what we've done is we've combined the last 10 full frame images we got together. We put the high resolution images on top of the lower resolution images. And this has been orientated so Dimorphos' north pole is up. And we actually have an approved naming scheme for the features on Dimorphos that has been approved by the International Astronomical Union. And since we're smashing into things, the theme is percussion musical instruments. So these are the features that we've named so far. All of these have saxum after them, so it's atabaque, saxum. Saxum is Latin for stone or rock. So here we are zooming in on the impact site. We know from reconstructing the spacecraft's trajectory that the SmartNav system I talked about earlier did a really great job. And we actually impacted Dimorphos very close to the center of the asteroid. The predicted impact point is shown inside that little circle on the right between the two boulders. And if we zoom in again on this, this shows the footprint of the DART spacecraft with its big, long, rolled out solar arrays that stretch above and below the main spacecraft bus. And this shows where we actually impacted onto Dimorphos. The largest boulder, which is Atabaque Saxum, is about 6.5 meters long and about 2 meters above the surface. And we've determined that the solar array first hit Atabaque first, then the other solar array just glanced off Bodrum Saxum, which is also about a 6-meter boulder to the north. And then this was followed by the main spacecraft bus, which is sort of 90% of the mass of the spacecraft contacting into the surface. So DART did its impact job really very well. It streamed back some really great data from the final minutes before impact, but that's the end of it. We smashed the spacecraft into tiny pieces. There's no more data coming from DART. So what did we see from the ground after the impact, and how are we going to go about making the measurements of this change in the orbital period? So we assembled a large team of people and actually had telescopes on all 7 continents to observe Didymos. One of those 4 contracted observatories is Las Cumbres Observatory, which has a network of telescopes all across the globe, and they are highlighted here in orange. Also, we have radar observatories at Greenbank and Goldstone, which is just down the road in the Mojave Desert. And in addition to all of our ground-based assets, we also have space-based assets in the form of Hubble, JWST, and the Lucy mission, which is actually on its way out to the Trojan asteroids. And all of these observed Didymos after the impact. So Las Cumbres Observatory, which I work for, has a network of telescopes all across the globe. So we have two 2-meter telescopes. One of these is in Maui in Hawaii, and one is in Siding Spring in Australia. We have 12 1-meter telescopes at Australia also, South Africa, Chile, Texas, and Tenerife. And we're hoping to get 2 more to Tibet next year. We also have 10.4-meter telescopes at the same sites. These are primarily used for education. All of these telescopes are robotic, so nobody's at the telescope making observations, and they're all remote, so they get their instructions on what to observe from here in Santa Barbara. The network can respond to new observation requests if something exciting happens, like that supernova that was just recently discovered, and this can happen within 10 minutes. Also, we can monitor objects around the clock because we have a global network, and this was of great importance for DART and the Didymos observations. So on the left is 3 of our 1-meter telescopes. This is at our site in Chile, and on the right is a view of the back of one of these 1-meter telescopes that shows our main CCD imager, which is in the sort of the back box. And there's also 2 big instrument and control crates on here. And there's also an auto-guided camera, which you can't see because it's hidden by the main camera. And we actually used these FLI auto-guider cameras to make time of impact observations. So DART's time of impact was actually during the night at our site in South Africa. And so we decided we'd use all 3 of our cameras to take lots of short exposures and try and observe the ejector cloud. On the right here are some simulations that were done before the impact of what the ejector cloud might look like at 1 hour in the top row and 22 hours in the bottom row after impact. These simulations were done for Hubble, so these boxes are only 41 arc seconds across, so we didn't really expect to see very much from the ground at all. We thought the sort of central pixel might get a bit brighter. Fortunately, DART massively overperformed. These is an animation of 50 images from those FLI autoguided cameras at South Africa just after impact. And we can see this huge increase in brightness and this huge cloud of material that came off after the impact. And we've also got 2 stills from 12 minutes and 15 minutes after the impact. And over the following days, it just kept going, and it just grew this huge tail, and we basically turned the asteroid into a comet. Our colleagues at the Atlas Project also had telescopes down in South Africa, and they saw the same big giant plume after impact that we did. We had observations from Magdalena Ridge in New Mexico and from Arizona. We had observations from our own LCO observatories in Chile and South Africa and Tenerife and Texas. It was observed from Europe, from Israel, from New Zealand, and I say even from Antarctica. And not only did we have all of these ground-based telescopes capturing it, several space-based observatories, including JWST and Hubble, captured detailed views of the DART impact as well. These images, so this is Hubble on the left and JWST on the right, show observations of the system several hours after the impact with the material coming off. And this tail just kept growing and growing. So this is an animation of many Hubble visits covering 18 days. This starts from 1.3 hours before impact out to 18.5 days afterwards. And we can just see this material coming out in several directions. And then it settles down into this tail, which then seems to sort of split into 2. And this set of images is covering the first month from one of the DART investigation team's programs on the 8.2 meter VLT down in Chile. We actually managed to get all 4 8-meter VLTs pointing at Didymos on the night after impact. And this month of images shows, I say, the ejector, which produced this sort of fan, and then it turned into a tail. which then stretched off the images. And that tail is still there. This is from the 4-meter Lowell Discovery Telescope, nearly 6 months after impact and close to when we finished observing it from the ground. The tail's not really visible in individual images anymore, but this is a 20,000 second stack, and the tail is sort of 70,000 kilometers long. And the tail is still just about visible in the stacked Hubble images. We actually had a Hubble visit this week, and we can still see the tail, and the Hubble observations are going to continue until early July. So this ejector in the first few minutes, and then that tail over the next several months, was plenty exciting, much larger and much longer lasting than anybody expected ahead of time. But if you remember back to the start, NASA Administrator Nelson announced that DART has successfully changed Dimorphos' trajectory. And you might also remember that I said we were going to change and measure this orbital period. So how do we go about doing that? So this animation shows Dimorphos, the smaller asteroid, orbiting around Didymos, the larger asteroid. And when we measure this from telescopes on the ground, we don't see them separately. We can only see the combined brightness of the two objects. And when we measure that, we get a light curve, and that's shown schematically in the bottom. As Dimorphos goes around Didymos, when it passes in front of Didymos, we get a small dip. And when it passes behind the back of Didymos, we get larger dips. We could do this before the impact, and then when we do it after impact, then this small change in period initially isn't very noticeable, but over time, this change in period accumulates to the point where these eclipses no longer happen at the same time that they did beforehand, and the position of them has shifted considerably. So before DART's impact, Dimorphos went round in 11 hours 55 minutes. After the impact, it was going around in 11 hours 22 minutes. And this animation shows a magnified view of what Dimorphos's orbit around Didymos would look like as seen from the Earth about a week after the impact. So we can see Dimorphos going around Didymos, and as it goes into Didymos's shadow, we get this deeper dip, and then half an orbit later, it casts a small shadow onto Didymos. You can just see it briefly there. And so by measuring the time between these small dips, we can measure the new period. And this is the actual data. This is a sort of zoom out view of a little over a week of the data. And if we had not changed Dimorphos's period, we would expect the eclipses to occur on the same 11-hour 55-minute time clock as we had before. And that's shown by the gray arrows. If we look at two of the zoom-ins of the particular days down in the bottom, you can see that the dips are not occurring where we predict them to be by the gray arrows. They're occurring at these new positions, and that's indicated by the orange arrows, and this is the new 11-hour 22-minute orbit. So the actual light curves are even more complicated than the sort of shown in that quite zoomed out view, and definitely more complicated than the sort of the cartoon illustration. So these are real light curves from LCO. There's a lot going on in here, so I'm going to break them down for you. So this full light curve at the top is the raw brightness that we observe straight out of the images. And so this is Didymos and Dimorphos combined together into a single point of light in our telescopes. Didymos itself has its own rotation period. It rotates in about 2.26 hours, and it's also quite an irregular shape. So it produces its own light curve, which is shown here down in the bottom panel C. And what we need to do is we need to model and fit this primary rotational light curve and subtract it out of the full light curve at the top. And this then gives us the orbital light curve, which we're actually interested in. And you can just about see the small dips in here which are the eclipses. So these are the actual primary and secondary eclipses. The light curve on the left is before impact. That was taken in July 2020, end of July 2022. The one on the right is taken from January in 2023 after impact. Not only did we have measurements of the change in Dimorphos's orbital period from the optical light curves, but we also had independent measurements from the Goldstone planetary radar. This is DSS-14, the 70-meter antenna and radar transmitter that's at Goldstone out in the Mojave Desert, and is normally used for talking to spacecraft, but can also be used to take images of asteroids. So this is a radar image of Didymos and Dimorphos. It's a little different to an optical image. Across the horizontal axis, we actually have Doppler line of sight velocity, and then on the vertical axis is range, basically distance from Earth and from the radar. If you remember, I said Didymos is rotating with a 2.26 hour period, and that causes it to broaden in Doppler space. So Didymos forms this elongated set of pixels in the center. Now, you're going to have to take my word for it on here, but this small group of pixels down here is not noise. This is actually Dimorphos. And part of the reason why we know it's Dimorphos is because we know what the orbit of Dimorphos is. And so we can make predictions about where Dimorphos should be if we hadn't changed the orbital period. And the fact that we're getting this group of pixels in a different place is proof that we changed the period. And we can actually track Dimorphos. So this is a set of images from October the 9th. And from these and longer sets of images, we can actually see Dimorphos orbit, and that's how we know this small group of pixels is actually really Dimorphos, and it's not just a bit of noise in the data. So by measuring this change in period from telescopes on the ground, such as those of LCO and from the radar, we know that we changed the orbital period by 33 minutes. This is some 25 times more than our minimum requirement, which was 73 seconds. We can see from all of the ejecta that came off and made that cloud and tail that we must have got extra movement of Dimorphos from the recoil of all of that ejecta. And it's vitally important that we know what this extra momentum factor, which we call beta, is for planetary defense planning purposes, since that's going to tell us exactly how many times and how hard you would need to actually impact a threatening asteroid. We expect values of beta from 1 to 4 from tests like this one that are done in the lab on the Earth, but we can't get up to the full impact speed in the lab. This impressive looking footage is actually from only 2 kilometers per second. The only way to know for real what it is to do the experiment with DART. And so the different values of beta are shown schematically here. So for beta equals 1, we get no ejecta and we get a small increase in the momentum. If beta is close to 2, then we get some ejecta coming off and we get a moderate increase in the momentum. And if beta is as large as 4, then we get a large amount of ejecta that gets thrown out of the crater caused by the impact, and a very large amount of additional momentum when we move the asteroid a lot more. So based on this measured period change and our best estimates of the size, the volume, and the density of Dimorphos, we can get a value of this beta of 3.6. And this shows that we got a lot of extra momentum and deflection from all of that ejecta. This number is going to be greatly improved once the Hera mission gets there. And I'll talk a little bit about the Hera mission later. And it's actually going to go into orbit and actually measure and weigh all of Dimorphos. So all of these results on the impact, the measured period change, the ejecta we saw in the Hubble images, and this determination of how much momentum transfer we've done were all published in a special edition of Nature back in April. All of the articles are open access, so they're actually freely available, unlike normal for Nature, where you have to pay large sums of money. So the observers part of DART is over. We've delivered all of our data to be reviewed and archived and made available for future researchers to use. The rest of the DART team is still hard at work modeling and refining the asteroid shape model. They're also running big supercomputer simulations to try and understand the dynamics of the impact and what it can tell us about Dimorphos and about asteroids in general, so that we know both more about how asteroids formed and evolved, but also how best to deflect one if we need to do so in the future. So I said right at the start that we were on a long journey through figuring out how to defend the planet, and this has been a journey of international cooperation. And this is really important because defending the whole planet is clearly an international issue. So as part of the Asteroid Impact and Deflection Assessment collaboration, we took the first step with DART. This successfully demonstrated the kinetic deflection technique. Next October, ESA's Hera mission will launch on its 2-year journey out to the Didymos system. And these two missions really complement each other very well. In 2022, DART collided with Dimorphos. We got limited views of the actual collision itself from the small Leisure CubeSat that came along on the mission. But the measurements of the orbital period change had to be done with telescopes on the ground, as you just saw. Hera is going to launch in 2024, and it's actually going to rendezvous with the Didymos system rather than just smashing into it. Hera and its two CubeSats, Juventus and Milani, are going to fully investigate the aftermath of DART's impact, and they're going to fully map, measure, and investigate both asteroids. The Juventus CubeSat actually carries a radar, which will allow us to see inside both asteroids. And there's also a thermal, infrared, and a hyperspectral imager that are actually going to be able to map the minerals on the surfaces of the asteroids. And Hera is really going to give us this key data to develop the asteroid deflection technique into a well-understood, scalable, and repeatable tool we can use. So finally, DART is NASA's first planetary defense mission. It was a very successful test mission, as we've seen, and it's proven that we can deflect an NEO with a kinetic impact emission. We measured the change in Dimorphos's orbital period with the telescopes of Las Cumbres Observatory and other telescopes around the world, and we measured it to be 33 minutes, and this was much more successful than we expected beforehand. Myself and the other ground-based observers have been really busy observing Didymos. We've collected over 42 days worth of telescope data. We've been really busy analyzing all of the light curves, but there's still a lot more of the data to analyze, both from Draco and DART and from the ground-based data. We've determined exactly how much extra push all of this ejector gave to Dimorphos, but we're still working to refine that number, model it, and explain it in terms of the material properties of Dimorphos, and so that we can understand asteroids much better. Finally, next year, Hera is going to launch on its 2-year journey out to the Didymos system, and it's going to provide a full characterization of both asteroids in the system and see exactly how much of a mess we made and how big the crater is. And this is going to allow us to have a much better idea of the impacts of a kinetic impactor like DART if we ever need to deflect an asteroid for real in the future. Thank you very much. I'll take any questions if people have them.
Thank you very much, Tim. That was a fascinating talk about a fascinating mission and extraordinary results. Thank you again. Now the floor is open. If you have any questions, feel free to send that through the Q&A. We already have one. The questioner is talking about the Asteroids. As for asteroids, we can calculate orbits ahead of time, but what about comets coming in from Kuiper Belt or Oort cloud? Can we calculate their orbits enough with in advance enough?
No, in general. That's what my sort of other hat is involved in. As Reza said at the start, I'm co-lead of this thing called the Look project, and so what we're doing with that is we are trying to characterize and understand new comets that are coming in from the Oort cloud for the very first time. The reason why we're trying to do this, and I should say that we're trying to understand how these comets turn on and start becoming active and develop the tail. And the reason why we're doing this is because ESA is going to launch the Comet Interceptor mission, and that's actually going to do a flyby of one of these new comets that are coming into the solar system for the first time. And in order for this mission to work well, we have to know how comets like this behave. And so that's part of the project that we're sort of doing with LCO's telescopes. Fortunately, in terms of impact threat, comets are much less, they cause much less risk than asteroids do. The vast majority of the impact risk comes from asteroids. This is quite fortunate because comets coming in from the Oort cloud are moving really, really fast. They can be sort of 70 kilometers a second as opposed to the 10 or 15 kilometers a second of an asteroid. So if one of those were to aim for us, those really would make a spectacular mess.
Okay, thank you. And the next question is about the spin. Would an increase in spin by the collision reduce the change in orbital velocity? Are they two related, the orbital velocity versus the spin?
Yeah, this is one of the really challenging things that we're still working on at the minute. The dynamicists on the team were very non-committal in terms of what we would do to the asteroid afterwards. It's possible we've set dimorphous librating, so it's basically wobbling backwards and forwards. Unfortunately, we obviously don't have DART anymore because we smashed it into the asteroid. We don't have anything, Hera is not going to get there for another 2 years. And the asteroid is getting fainter and fainter and is now unobservable from the Earth. And so we're trying really, really hard to try and tease out these sort of subtle effects from the light curves and the measurements that we've got so far. But yeah, a lot of this stuff is coupled together. The shape of dimorphous, the eccentricity, if there was any, whether it's librating, even just basic things like, how far apart are the asteroids? It's, all of this is sort of coupled together because we don't have any yardsticks at the asteroid that tell us how big things actually are. And so it's an iterative process. You can work out where you think the spacecraft was, and that tells you how far away you were from the asteroid, and that tells you how big the asteroids are. And you keep going around this loop, and eventually you converge on an answer. And hopefully it'll be an answer that Hera will not prove us wrong in 3 years' time when it gets there.
Okay, thank you. And can you tell us about the design of the spacecraft itself? It doesn't look like it's specially made to collide. It's a cube. Did you add any extra weight to it in order to make it better for the collision? Doesn't it need to be maybe with a different shape?
No, so DART was built basically as a low-cost technology demonstration mission. DART is not a science mission. This is why we are an investigation team and not a science team. It's a planetary defense test mission. And so the spacecraft was, used relatively cheap components for a space mission and also tested out a lot of technology. So the spacecraft was about 700 kilos at launch, but most of the momentum from the collision is not coming from the mass. It's, you know, high school physics, it's half mv squared, and the velocity is very high. As I say, you know, it was sort of 6 kilometers per second. So there's not much that we could do, you know, to make the spacecraft heavier and still launch it on an affordable rocket. Originally, DART was going to be a rideshare along with another mission, and we would have used the Ion engine to get us out to Dimorphos. The plans changed, and because of the nice folks at SpaceX making rockets cheaper and cheaper, it was more cost effective to get our own rocket. So there's pictures of DART looking very silly and small inside the Falcon 9 fairing from before launch. It's just this small cube with its rolled up solar arrays at the bottom of the fairing.
Okay, I see. And the trajectory was, if I understand it correctly, compared to some other missions, was not as complicated. It was to give it enough momentum and then go directly smash. No orbiting the system, nothing, just from Earth to smash.
It was a very quick mission. You know, basically 11 months from launch straight to impact. Yeah, there were initially, there was sort of plans to maybe fly by something else on the way. But in order to, you know, ensure that the mission was going to succeed and we would definitely get to Didymos and we would definitely impact, it was just like, right, no, we'll just keep it simple, just aim at the asteroid, don't do anything else, just hit.
Okay, thank you. Now, you did mention about the scientists' estimates about different size of asteroids which exist in the solar system. Now, the question is, if you haven't found those, how did you make the estimate of how many asteroids of a certain size are there in the solar system?
Right, that's a good question. So we can measure the asteroids that we've seen. We can get estimates of how big they are from how bright they are, if we make certain assumptions about what they're made of and how reflective they are. And so this allows us to work out how many asteroids we've actually seen of a certain size. The next thing you have to do is you have to sort of model your detection survey and try and figure out how many asteroids you're missing of a certain size. So you sort of say, okay, if we have this many 500-meter asteroids and the survey operates like this, how many of those that we know we put in did we actually find? And that allows us to assess our completeness fraction. And this unfortunately gets, you know, more uncertain as we go down to sort of smaller sizes. From the really small ones, like, you know, we can also count craters on the moon, and we can count the really small things that hit the upper atmosphere. And if you plot the number of these things per size, you get what's called a power law. And so from this, we can basically estimate how many objects we expect to find of a particular size.
Great, thank you. Now, a question is about, two questions about the estimate. So you said that the system was not seen directly before, so you only had an estimate of the size of Didymos, and then you confirmed when the spacecraft reached it, it was 150 meters, around that much. So what was the previous estimate, and how well did it match the actual size?
Yeah, so we had, so from the last time Didymos was close to the Earth, which was back in 2003, and this is when we actually found Dimorphos. By looking at the light curves, we could see the dips, and that's when we first found Dimorphos. From At the same time, we also had estimates of the size from the radar images that were taken at the size, and that's how we knew that Didymos was about 800 meters. And we had actual images of Didymos. And so from that, it's sort of Kepler's laws. You know how massive roughly Didymos is. You know how long the orbital period of Dimorphos is. From the size of the dips in the light curve, you can get an estimate of the size of Dimorphos, and the estimate was about 160 to 170 meters. But there was quite a lot of uncertainty on that because we didn't know what shape Dimorphos is, and if it's a long elongated cigar shape and it's rotating round, you might be seeing narrow end on or wide side on. If it's eccentric, it's also going to be changing distance. So we didn't really have a good sense on that. And we also had no idea of the shape of it. So the spacecraft folks ran a lot of simulations of SmartNav, of putting in different asteroid size and shapes and checking that the spacecraft was actually going to be able to detect it and aim for it.
Thank you. And the next question involves the estimate on the impact. So did the change in orbit due to the impact match the expected change from initial calculation?
No, it was much more successful than we predicted. As I said, we had this minimum requirement that was set as the mission goal of at least 73 seconds. The dynamicists and the modelers reckoned on 600 seconds beforehand. We actually ran a poll among the whole investigation team before impact, and the predicted answers were all over the place, from 2 minutes to an hour. So the final one of 33 minutes was, almost a factor of 3 greater than the best estimate we had ahead of time, because we got so much more material came off than we expected. Nobody expected us to turn it into this comet with this long tail that was going to be there. We thought there was going to be some debris and it might take a while to sort of clear out, but yeah, this amount that came off, it was particularly crazy. We were sat in the conference room at LCO, watching the data come back in, and we just saw this big thing come out on the screen. And it was like, what the earth is that? It's like, is that real? That can't be real. Unfortunately, because we have 3 telescopes down there, we could check the other telescopes. And it was like, no, that's happening in all 3 telescopes at the same time. That's real. Holy cow. So that was a quite incredible moment as we saw this huge plume of stuff come out.
Incredible, thank you. Okay, now let's switch to the crew on the ground. Do we have any questions from the in-person audience?
Yes, I see one person who's had his hand up. Sir? The question was, what were the relative velocities of the impactor and the asteroid at the time of impact, and what was the mass of the impactor?
Let me do the last one first, because it's so the spacecraft was about 600 kilos at the time of impact. We used a little bit of fuel. We had both hydrazine and xenon fuel on board the spacecraft. The xenon was for the ion engine, which we didn't use in the end. It was turned on briefly, but we did use the hydrazine for course corrections, so that used some of the fuel. Also, we had the Licia CubeSat at launch, and we ejected that 10 days before, so that took some of the mass. So yeah, the spacecraft was around about 600 kilos, and as I say, it impacted at 6 kilometers a second.
Another question?
Yes. They talked about, if you will, the first goals by the bomb. How big a type of bomb did they contemplate launching the asteroid?
The question is, you wanted the equivalent as a hydrogen bomb?
No, I'm talking about they talk about hydrogen bomb. How big is hydrogen bomb? Maybe 5 or 6 megatons.
The question is, if you're using a hydrogen bomb to deflect an asteroid, how large a hydrogen bomb would you be considering?
You don't actually need a very big one. From those that have sort of done these simulations, so people like the folks up at Lawrence Livermore National Lab who model nuclear bombs, you don't actually need a particularly big one to do it. A couple of 100 kilotons is normally enough because you can get it very close, and you actually vaporize a lot of the surface, and this effectively acts as a rocket engine. The biggest problem is actually a political and legal one. According to the UN Charter for the Peaceful Uses of Outer Space, you are not allowed to put nuclear weapons or detonate nuclear weapons in space. This is a topic that comes up at the Planetary Defense Conference, as whether you would get an exemption for this in the case of
self-defense,
trying to protect the Earth.
I think I saw another hand. Sir, did you have one?
On the graphic on the screen, look at both the asteroid was going clockwise and then the spacecraft is counterclockwise, both of them counterclockwise, and it sort of looked like it sidled up to it before impact, whereas if we'd have launched it the other direction, it seems like it would have been a much bigger slam. Is there a reason that they do it clockwise into counterclockwise? Is that much more smooth?
The question is that it looked from the graphic as though the spacecraft was essentially following the target, and so hitting it from behind, as opposed to hitting it head on, where the impact might have been stronger. Was there a reason for that?
That might have been a misleading graphic in that case, because it definitely was head on, and this was deliberate. So the sort of geometry of it is that Dimorphos came out from behind the back of Didymos, and then the spacecraft ran head on into it. This was deliberate because we wanted to shorten the orbital period and make Dimorphos orbit closer to Didymos and not lengthen the orbital period and make it orbit further away. And this was from a planetary protection point of view. We didn't think it was at all likely that we would knock Dimorphos out of its orbit and send it shooting away from Didymos, but we didn't want to take the risk. So the trajectory was designed so that it would be a head-on collision and we would shrink the orbit rather than expand it.
Thank you. Did I see another hand? No, I think that we've answered the questions from. Was there one more? Okay, one more. The question was, what was the final orbital period when the 33 minutes was subtracted?
So the final orbital period is 11 hours, 22 minutes. The change in orbital period is 33.15 minutes plus or minus 0.5 seconds. That's how accurate we've actually been able to measure it. We worried a lot that we wouldn't be able to get down to the 7.3 second error budget, but we've actually, we've now got it down to half a second with the latest orbit.
That's great. Thank you. Any other? Okay. Somebody is up in the darkness, up at the top of the room. I'm sorry, I didn't see his hand before. Yes, sir. The question is, was there a backup plan in case you missed?
Yes, there was. So the mission operations team at APL, who built and ran the spacecraft, they went through a lot of dress rehearsals of what would happen. They simulated a whole bunch of potential asteroid shapes, I think including like donuts in case, we sent the spacecraft straight through a hole in the middle. So yeah, there was a plan. It would have been quite a risky plan in the end if we had actually missed it. What we could potentially have done is turned the ion engine back on again and done a very long burn with the ion engine, and we would have come back to Didymos in, I think, 2026. But fortunately, it all worked fine, and because there was but it was definitely nerve-wracking because it's the first time we've ever done this.
Great. Anybody else I missed? Okay, looks like we got anybody. Thank you very much, and I'll turn it back to you, Reza.
Sure. Now we have another question. It's about the spacecraft itself. So can you tell us how many course corrections were made between Earth and when the auto tracking system was turned on?
I believe it was 5 in total. I think that was it. And the final trajectory correction maneuver was something like 24 hours before impact. And then SmartNav took over at 4 hours out.
Okay, perfect. Thank you. And the last question I have here actually involves the graphics that you have here. So can you tell us a little bit more about how the dynamics between the planets work and how Jupiter is protecting the Earth and how these things how these asteroids make their way into the inner solar system and how Jupiter is protecting that?
Yeah, so this is an area of active research, along with the people that do the modeling of how many asteroids and NEOs we have in the solar system. There's another group of people, also the dynamicists, that try and work out how the asteroids get to where they are, because we know they weren't formed there. They can't be formed on these Earth-crossing orbits. It's a very complicated dynamical picture, but basically it involves gravitational interactions between the planet and, as you say, primarily Jupiter, because it's the most massive planet in the solar system. And in terms of sending NEOs into Earth-crossing orbits, there's what's known as the nu-6 resonance of Jupiter. It's basically a resonance with Jupiter. And it's basically responsible for provides basically small tugs to the asteroids and will eventually kick them out of the main asteroid belt and send them into Earth-crossing orbits. There's another effect that acts on asteroids that are quite small. It's kind of a weird one. It's a thing called the Yarkovsky effect. And the way this works is sunlight heats up one side of the asteroid, and the asteroid is rotating, and then that sunlight is then re-emitted by the asteroid in a different direction. And this basically acts as a very small thruster, essentially, and moves the asteroids around in their orbit over millions of years. And this is something we can actually detect on near-Earth objects, particularly with things like radar, which gives us very, very precise ranges. And so we can actually measure this additional Yarkovsky acceleration. And this also works to shape the asteroid belts. It causes the asteroids to group into families over time.
Okay, perfect. Thank you very much. So that covers all the questions online. Are there any more questions in person?
I think there's just one final question here, which is talking about how much the orbital eccentricity was changed by the impact. I wish I could give you an answer to that, but we can't actually get that number out yet. We're still trying to model all of the times of measurement, all the times of eclipses. As I explained earlier, this is sort of coupled in with the sort of shape model as well. So we don't actually have a measurement of the orbital eccentricity yet. We might be able to get some observations of Didymos next year in 2024, but it's much fainter. It's only going to be the eclipses are only going to be detectable from like 4 or 8 meter telescopes. But it's possible if we can get some more eclipse determinations next year, we might be able to nail down whether we actually put Dimorphos onto an eccentric orbit. The fits show at the minute maybe small amount, but it's still quite uncertain.
Perfect. I actually see one more question. I don't know if it was answered during the time that I was disconnected or not. But the question is about the 2005 impact on Tempel 1 comet.
I did answer that in the chat.
Oh, you did, okay.
But to sort of relay the question, so the person was asking, so Tempel 1 was smashed into by the Deep Impact spacecraft, which was about 900 kilos. Well, it fired a projectile into the comet Tempel 1, and the questioner was asking whether we'd deflected any change in its orbit. The answer is no. It's much more difficult to measure the orbits of comets more precisely. Comets have all of these jets shooting out of them, which causes the orbit to move around a little bit. And also Tempel 1 is a much bigger object. It's several kilometers in size. So any deflection we would have got on that from the spacecraft impact would have been tiny. So we've not been able to detect that.
Okay, and I see one final question here about Oumuamua, this cigar-shaped object. So do we have any specific defense plans for that kind of objects, or does it matter? Does it really matter the shape?
Yeah, the shape would matter. If you imagine trying to do, a dart light deflection mission on a rapidly rotating cigar, that would definitely be challenging. And this is something where, NASA is sort of thinking about for the future, not specifically for Oumuamua. Those objects are so rare. We don't need to worry about those. The upcoming big sky surveys like Rubin, which is going to come online in the next couple of years. We're hoping, fingers crossed, that we might get one of these Oumuamua type objects per year, if we're really lucky. So they're not something we need to worry about. But this idea of doing a fast reconnaissance mission of something we don't know the size and shape of at all ahead of time is something that we're sort of thinking about as a follow-on from DART and from Hera.
Okay, perfect. That was it all. Again, Tim, thank you very much for a great
Reza,
talk.
I think we had one last question here.
Sure.
Okay.
Question? The question was whether there has been a lot of debris accumulated in the Lagrange 2 point that might be a hazard to the James Webb.
No. So Didymos's orbit is, it's still, although it was relatively close to the Earth at the time of impact, it was still 7.1 million miles away. It's well outside the Lagrange points. Virtually all of the ejector from the impact will have left the system. Some of it fell back on, but the gravity of the asteroid is so weak. I mean, it's not even walking off the surface. It's, yeah, the actual gravity of the asteroids is incredibly weak, so it won't hold on to any of the material. It just streamed off into space to form that tail.
Great. Thank you. Any others that I missed?
There was one
think-
additional comment in the chat, which was asking about whether there was a recent asteroid impact on the moon. I don't know of one, but I know people do find them all of the time. I mean, one of the nice advantages of modern digital technology is people can point these basically video cameras at the moon and just like monitor it for impact. And I know amateurs do find impacts of small objects on the moon every so often. I don't know exactly how often, but yeah, stuff is definitely still hitting the moon.
Perfect. Thank you very much, Tim, for a great talk. And I would like to thank everybody in the audience for being with us. Please check the calendar on our website for all our upcoming events at ocastronomers.org. Thank you for joining us, and we wish you great times ahead. Bye-bye, everybody.